In these last two videos, we'll be completing our tour of things people do with programs by building a small compiler. So to do that, we need to build a little model of a machine that's going to represent like the computer that we're going to compile our little language of AXPs and BXPs down to. Compilers are intimidating. My hope with this exercise is to A, show you some techniques, and B, to sort of like demystify them, make them a little bit less exotic and intimidating. So let's get started. So in general, the way a compiler works is it takes a program in a source language as input and produces a program in a target language as an output. Now, like, typically, the source language will be high level, like something a human would write, and the target language would be low level, like machine code or assembly or something. But like all kinds of stuff happens. People do all kinds of crazy translations, and they're all compilers, right? I think it's just like the nomenclature here is really silly. There's one that I find particularly silly called transpiler, which is like a blend between a translator and a compiler. And like, I don't know why people need all these names. You can call them all compilers or translators or whatever, and people will know what you're talking about. If you call something a transpiler, then people will not think you know what you're talking about. So just like a pro tip there. Uh, right. So the main motivation that people have for compilers is they want to make their programs go fast. So I'm going to tell an anecdote that a friend of mine who's a professor at the University of Maryland tells, and hopefully he'll forgive me for telling it. So David Van Horn is a professor out there, and he tells the story when he explains what a compiler is. So like when his dad was a kid, when David's dad was a kid, they would have races at lunchtime in the school cafeteria to see who could finish their lunch fastest. And like all I can really say about this is like, wow, kids are pretty weird, huh? That's gross. Really, like, who wants to? That's anyway, whatever. And there was one kid that his dad knew who before they started the race would like on his tray like mash everything together. He'd like get the potatoes and like whatever it is and like mush them all together and like pour his juice on it. So like it was all in one spot. And so then he could just like shove it all in his mouth because it was all sort of in one big gross pile. And that kid wrote a compiler. Okay. So let's see what we want to have you do. So in this video, I really want to just talk about the machine we'll be compiling to, which is a very, very simple stack machine. So what's a stack, you might ask? Well, in our setting, a stack is just a list. So it's a machine that keeps a list of like things and operations that it's going to do. So stacks are a very, very old idea in computation. In fact, in like the 70s and before, HP made these like the most powerful calculators were these postfix calculators where they would be programmed using a stack. So if you wanted to evaluate a program like this, first do 2 times 3 and then do 3 times the quantity 4 minus 2, you'd write it out in sort of stack form where it's like push 2 and 3 on the stack, and then multiply what's on the top two numbers on a stack, and then push 3 and 4 and 2 on the stack, and then subtract the second number on the stack from the first number on the stack, and then multiply those two quantities, and then do a plus. Okay, hard to see what's going on just from here. So here's a diagram. Okay, on the right, we have the program being evaluated, and the contents of the stack we have on the left. So here's the program. And then we're going to evaluate what's on the stack from left to right. So what we did first is we pushed the 2 on. Then we pushed the 3 on. And then the multiply says, okay, take the two top things on my stack and multiply them. Right? And here we don't really get to totally see which order it's happening in. Right? Like, okay, not totally clear. But it doesn't matter because times is commutative. So we'll get 6, right? Those two elements of the stack have been consumed and the operation has been performed. We get a new element on the stack. Then we push a 3 on, and then we push a 4 on, and then we push a 2 on, and now we're here. And now we do the subtraction, and we can see, okay, we went from the stack 2, 4, 3, 6 with the operation minus to the stack 2, 3, 6. Okay, we must have subtracted this number from that number. Right, the top thing of the stack got subtracted from the second to top thing on the stack. Then we do a time, so the 2 times 3 happens, so then our stack is 6, 6. And we do a plus, and we get 12. And we should check our work. Is this the answer that we expect? Well, yeah, this will evaluate to 6. And then 3 times 4 minus 2, that's 3 times 2. This will also evaluate to 6, and we'll sum them, and that'll be 12. So the steps even match up. So one of the nice things about a stack machine is that you don't need any sort of precedent stuff. You just go in stack order. So the job of our compiler will be to take the tree of our program and collapse it into a linear stack form where it can just run. Okay, what's the language of our stack machine? So here I just wrote the number or just wrote the operation and just said, oh, and then we do it. But in practice, in Coq, we'll define a data type for it. So here's our instructions. Nothing sinister about it. Stack instruction is what the name is meant to be. And we're going to give ourselves 5 different instructions. So one instruction says push, and then it gives a number, and it says push this number onto the stack. So there's English descriptions of each of these up here. The next one, load. Don't know why my screen flashed. The next one, load, says, okay, load this identifier from the store, from the state, and push it onto the stack. Plus says, pop the 2 top numbers from the stack, add them, and push the result back onto the stack. Minus is the same but for subtraction, and mult is the same but for multiplication. So the program we saw above, this program, we would write like this. Push 2, push 3, multiply, push 3, push 4, push 2, subtract, multiply, add. Okay. So the first bit of your homework here has you defining the stack machine. We want you to do it in 2 parts. First, we're going to write a part that runs the instruction. And then we're going to write the part that just runs the whole program, which is a list of these instructions. Okay, so what does the instruction part do? Well, the type here tells you, given a state, given a stack, and given an instruction, return a new stack. So you just have to implement, based on the current instruction, what you want to do for each stack. There's a bunch of advice here for how to work with it. I'm going to let you read it. The one thing I want to emphasize, because this is definitely a convention, it's a choice that we're making. If you're not sure, right, if your instruction is missing operands, like you get a plus, but the stack has what we call underflowed, your stack is empty or it has only 1 element on it, don't do anything. Just return the stack as it is. That's going to be our convention for what to do with these operators. And so here we have some suggestions about how to implement that in Coq. Okay, once you have that function, execute should really not be so bad, right? What are you going to do? You're just going to run each instruction in the program, updating the stack as you go for each recursive call. One thing I want to note, this run instruction function, we've written definition here, this does not need to be recursive. In fact, it doesn't particularly need helpers other than your usual arithmetic functions. Okay, that's part 1 of the homework. We've written some tests here. You can add the example we gave above to those tests. In fact, the file that you get should be updated to include that. And then your next bit of homework is about writing a compiler. I'm going to make a separate short video about that bit. Talk to you in a minute.